Hey, Hoodie Math coming at you here, live and in color. Hi, Carmen. Hi, Carmen. All right, it's time to get started. Guess what? Example 3 coming at you. Oh, Hoodie Math. So, free body diagram. We've seen this crooked spring before, so we have mass, we have our FK, we have our dampening force. So this is going to be case 1 when we're done with it. This is going to work out to be case 1. It's going to be a pretty complicated case 1 just because of the numbers we have to deal with. I'm going to try to simplify that. I'm going to go through all the parts again that we've done. So just to remind ourselves, this is our weight. So mass is equal to weight over gravity. And we're using gravity as 32 feet per second in each of our problems. So mass is equal to 16 over 32. We did this before. Mass is 1/2. M equals 1/2. All right. Next thing. K is equal to mg over our change in x. This is our change in x. And again, we've done this one before. That's 18. The next thing is we want to find how our C value changes with this new dampening force. So the dampener will exert a force of 17 pounds when the velocity is 2 feet per second. Remember, velocity. So FD is 17C times 2. That means C, 17 over 2 is our C. So once we have those three things, we can model our differential equation. 1/2 x double prime plus 18. Psych, that needs to be 17 over 2. That's where the C goes. 17 over 2, x prime plus 18. X equals f of t, which is 0 in this case, because again, there's no external forces. Remember, this is our next thing. The spring is initially displaced 6 inches upwards. So same as the previous problem. Our initial position is -6 over 12, upwards being negative. Previous videos, we've talked about defining our coordinate system with x is positive going down. So again, we have another value we can lock in. We also know the initial velocity was 1. All right, cleaning this up a little bit, I'm going to multiply by 2. That is a 17 there. 17 over 2. And then we're going to convert that back to r's, right? So I'm going to write that over here on the side. R squared plus 17r plus 36 equals 0. We have to use the quadratic formula next. So r equals negative b, negative 17, plus minus the square root of 17 squared minus 4 times 1 times 36, all over 2 times 1, which is 2. The inside ends up being 145. So we have R1 will be negative 17 plus the square root of 145 all over 2. And that's approximately negative 2.479. R2 will be negative 17 minus the square root of 145 all over 2. And that is approximately negative 14.521. Cool. So next thing, we need to write our equation. So our equation is x of t, and again, this is case 1. I probably should write out case 1 for you, huh? Case 1, c1e to the r1t plus c2e to the r2t. So in our case, r1, negative 2.479t plus c2 e to the negative 14.521t. I am going to go ahead and store these in my calculator. I'm going to store this as A, and I'm going to store this as B. Taking the derivative here, x prime of t equals negative 2.479 c1 e to the negative 2.479t minus 14.521 c2 e to the negative 14.521t. And again, naming this A and this guy B here in just a little bit. I'll show you that. Let's plug in our values so we can get some equations. Back to the x prime, x of 0 is negative 1/2. So taking this, plugging it in, negative 1/2 equals C1. It's going to be e to the 0. That's going to go away plus C2, because that's going to go away. Or this is going to go away once I plug in 0. So there's our first equation and the second equation. Second equation is, that's going to be 1, negative 2.479. Are you ready to make, no, let's not make the change yet. 2.479 C1, again, that's going to go away. Once you plug in 0, it's e to the 0, which is 1, minus 14.521 C2. All right, so I'm going to change these to A, B. And there's a reason I'm going to do that. I don't have to write all the decimal. I'm going to simplify things a little bit. So I'm going to carry on to the next page. So you ready? Let me copy these down on my new page. All right, here we go. So this is the system I want to solve for C1 and C2. A and B, again, A is negative 2.479 and B is negative 14.521. Again, I'll program that in my calculator in just a little bit and show you all that. But for now, let's go ahead and solve this. Just keep things simple. I want to make a negative A on top. So let's multiply this by negative A. I'm going to rewrite that below. Negative A times negative 1/2 would be A over 2. A times C1, it's negative A, so negative AC1 minus AC2 multiplied by negative A. Again, I'm multiplying by that decimal, but just in terms of a different variable to keep things clean. Cancels. 1 plus A over 2 equals, well, this is going to be B minus A C2. So I can divide by B minus A. I have 1 plus A over 2, and then B minus A. So that's what C2 is going to be. It's going to be in terms of these two decimals. And let's go back to the top, plugging it in. Negative 1/2 you probably can see this. I'm going to subtract C2. So I'm going to subtract this. Minus 1 plus A over 2, B minus A equals C1. So let's go to the calculator work now. I'll just show you how I programmed those in there. Again, A from originally, A was negative 17 plus the square root of 145 over 2. B is negative 17 minus the square root of 145 over 2. And again, I'm going to program those in my calculator now. So here we are. Alpha, y equals enter, negative 17 plus square root of 145 over 2. Store alpha A. Let's go back and copy it. I'm just going to change that to a minus sign. Store alpha B. All right, so now let's plug in my formula for C2. Alpha y equals 1 plus alpha A divided by 2, and then alpha B minus alpha A. There's our C2. All right, I'm around that now. 0.020. Let's write down C1. So C1 was just a negative a half minus this answer. There's C2. Again, rounding it. All right, so we have C1, we have C2. Again, alpha A was approximately negative 2.479. Alpha B was negative 14.521. So we have everything. Let's write our dang equation here. You ready? C1 e to the a, so it's negative 2.479t plus C2 was this guy, 0.020 e to the negative 14.521. And there's our final answer. And so that would be example 3. That's case, which ended up being case number 1. Didn't factor, went to a quadratic formula, which wasn't very nice. And we got this ridiculous differential equation to model this spring, the mechanics of the spring. You guys take care.